So a very quick recap of what we covered on Monday. We introduced electric field intensity. So later on in this class, it will be represented by this capitalized E and having a vector sign. So it is a vector field. What we covered was the two fundamental postulates. The first one is divergence of E is equal to the value charge density divided by the vacuum permittivity. Alright? So this is telling you if you have some kind of charge distribution in space, it will set up its own unique electric field intensity pattern. Just like what I'm showing you at the bottom. So if we have a positive charge, by the divergence relation, we know that divergence gives you outward flux of the field. So in this case, all the E fields, they have lines. Okay, so these are called E field lines. They are radiant, just like sunshine. Okay. And the second postulate is telling you nothing more, but it's further enhancing this picture. So your E field for a single charge is radiant, and therefore the field being created by these charges will be conserved. Now if you have a conserved field, then curl of this field will be 0, meaning it's conserved. Okay, you cannot gain work by walking in this field in a closed loop. Alright? Okay, so let's continue. Based on our understanding of these two fundamental postulates, we are going to introduce Coulomb's law. Coulomb's law is derived from a series of experimental data. So more than 100 years ago, people performed experiments, and based on their experimental result, they were able to come up with some equation, a law, to find out what is the quantity of the E field intensity for a given charge. So that's really remarkable, more than 100 years ago. So using Coulomb's law, I'm going to explain, and we can really now quantify the E field of a point charge. Up to now, we only have a qualitative description. And we don't really yet know what is the real value of the E field in space. Okay, so we're using Coulomb's law. And after we search the E field at the point charge, I'll give you the definition of Coulomb's law. Then we can use Coulomb's law to find the field distribution for some charge variation. Okay, so we are based on a point charge, and gradually we expand to some charge distributions. Right? Okay, this is pretty much what I drew on the blackboard. We have a single charge positioned in space. Don't ask me how the charge came here, okay? That's out of the question. So assume, magically, we have a charge sitting in space. We can just use its position, and we define it as the origin. Okay? Now, I have an observer like myself. I am standing some distance away from the charge. And from the first postulate, I know that if I have a charge, it emits radiant field lines. So basically, the field profile will be most resembled by a sphere. Okay? Okay? So if you have a given single charge, the emission pattern of the field is like a sphere. So before we start, this is something we also derived, right? Starting from the differential equation, we expanded into the integration form. So this is what we have. So this is telling you, if I have a given charge, then I know its field distribution as long as I know where the observer is. Right? So in this case, how to apply this equation? This is telling you, if I am standing here, right, some distance away from the charge, I know the charge is giving a spherical charge field distribution, and I know my distance. So basically, I'm asking, when I change my distance to the charge, how is the field intensity going to change? I want to know the relationship of the field strength, its magnitude. So how does that relate to this equation? The distance between me and the charge is described by this differential surface. Or in other words, when I'm away from the charge, the sphere is getting bigger, right? The radius is getting bigger, therefore the entire volume, the surface, is getting bigger. So therefore, for a given point, like my eyes, a given point, the field strength would certainly change as a function of a distance from myself to the point charge. All right? Okay, so now we know the essence, the meaning for this equation in integral form. Even though the charge remains unchanged, the field intensity, strength, its amplitude will change as a function of the distance from myself, an observer, to the point charge, right? So this E must be a function of distance. And that's what we're going to find out. And in doing so, we can quantify the field intensity, right? So how do we do that? So later on in this course, for the entire semester, the first thing you need to understand is, well, we spend so much time in learning about orthogonal coordinate systems. So the very first issue is, once you have a given problem, it has certain geometry. You need to find a proper coordinate system that is most convenient for your later analysis. Otherwise, why do we spend time in learning 3 different orthogonal systems? So in this case, we want to choose a proper coordinate system. And in this case, as we described, according to our anticipation, single charge emits like a sunlight, right? So basically, your structure, the field structure, the dependence to distance, would most be resembled by a sphere. So in this case, we would prefer to choose spherical coordinate system to work with. But again, spherical coordinate system is giving you the most complication because you have theta, you have phi, so you have 2 angular unit directions, unit vectors. So you have basically 2 arcs. All right? So I'm going to walk you through, although I bet all of you know the surface area for a sphere is 4 pi r squared. That is known from high school, but let me just walk you through and re-emphasizing what I highlighted on differential length, differential surfaces so much. Alright, so we are going to work in the spherical coordinate system. The first thing, to use this equation, you need to be able to formulate differential surface. And in this case, if I have an observer here, the differential surface is pointing in which direction? In the radial direction. So this ds, the differential surface, is a vector. It should be pointing in the radial direction. So once the direction is in the radial direction, its area must be determined by the differential length of the other two unit vectors, dl theta and dl phi. So dl theta, ask yourselves, what is dl theta for spherical coordinate system? It will be an arc. So for an arc, you need to know the radius. So for dl theta, the entire radius is used to span the arc. So it is basically r d theta. But in the phi direction, not the entire r is used to span the arc. It's only r sine theta. Okay? So for dl phi, again, I'm repeating this just to emphasize the importance of your clear understanding to differential length and differential surfaces. So dsr, pointing in the radial direction, its magnitude will be determined by these two differential lengths in the theta direction and in the phi direction. So now we know how to properly address ds for the single charge. We put it in. So the closed surface integration of E field intensity, this is to be determined. We are trying to calculate this. But the knowledge is the radiating field will be uniform in each direction. So basically, if we perform a closed loop integration, we know the total field strength. Okay? Now, this E, because ds is pointing in the radial direction for a dot product to be non-zero, in this case, the E field intensity is also pointing everywhere in the r direction. And that conforms to our assumption, right? For a single charge, the field lines are all radiant. For each line is pointing in the radial direction. And that's the reason why I'm using ER. The E field intensity for a single charge is everywhere radial. So I'm having the direction, I'm having its magnitude. To properly integrate over the entire spherical surface, phi, the integrand for phi is from 0 to 2 pi, right? 360 degrees. But for theta, in spherical coordinate system, theta is the angle of your radius to your z axis. So basically, theta only spans from 0 all the way to pi. So theta, the integrand for theta is 0 to pi. Right? Now we look at the things inside. AR is just, right, just 1. So there is no phi inside. So basically, d phi over the area, over the range of 0 to 2 pi is just 2 pi multiplied directly. Okay? So what we're left with is sine theta d theta integrated over 0 to pi. And that you know how to do. So I'm just showing you the result. So this is telling you 4 pi r squared is something we're very familiar with. It's just the surface area of a sphere with a radius of r. And that r here means the distance from the observer to the charge. So this is telling you the E field intensity amplitude is indeed related spatially, right? It is distance dependent. And that is equal to the charge contained divided by the constant. So through this simple example, I'm showing you, based on the knowledge of the E field intensity distribution being radiant, and it's conserved, we now finally know the E field intensity of a single charge with a very nice and precise quantitative description. So the field strength created by a single charge is inversely proportional to the square of the distance. Okay? Exact quantity would be having the charge divided by the square of the distance and then divided by 4 pi epsilon 0. So this 4 pi r squared is coming from the surface area of the sphere. Right? This is nothing new. I believe each and every one of you learned about the quantitative measure of a single charge. Right? So this is nothing new. This is only to refresh your memory, and I'm using this example to highlight the importance of being able to use a preferred orthogonal coordinate system for this equation. Right? Now let's continue. You might be wondering, how can I just assume the E field intensity is pointing outwards? Well, if I'm drawing this E field intensity, all these field lines pointing outward, I am making another assumption. This charge would be positive, right? Like on the blackboard. If I have a positive charge, I have fields emitted outwards. But on the other hand, if the charge is negative, then all these field line directions would reverse sign. Is that fact captured or allowed through our derivation? If I change the sign of charge, so now Q is negative, then this AR is also changed to a negative sign. Alright, so this is kind of included in my derivation. So this derivation result is valid. So if you flip the sign of the charge, the field flips sign as well. Okay, so now we're ready to define Coulomb's law. Coulomb, in fact, he measured the forces between two charged particles more than 100 years ago. It's very impressive. So he was asking the question, okay, if I have the first charge, Q1, right? The first charge is going to create its E field intensity distribution, like the one we just derived, Q divided by 4 pi epsilon 0 r squared. So he was asking the question, what happens if I bring a second charged particle, having charge Q2, and I allow it to sit somewhere, right? So the distance between the two charges is R12. In this case, what will be the resulting force experienced by the second charge? So his philosophy was, initially you do not have the second charge, you only have the first charge. So the first charge, its function is to set up some kind of field distribution. And then somehow I bring the second charge, right, from very far away, and I just let it go. So the second charge also sits here magically. Don't ask me why, okay? Because under static assumption, nothing moves, okay? So basically, these two charges are very well behaved. They don't move. They have a constant distance of R12. And he performed experiments to measure this force by changing the distance, by changing the charge amount. So he came up with this nice equation. Force 12. Listen carefully how F12 is defined. Having a subscript of 1, 2 means 1. Charge number 1 is setting up its field distribution to give a force on charge number 2. So E12 means the first charge is accounted for the field distribution. And this 2 is only to give the charge. Okay? So this means when you write F12, you understand about charge 1 is setting up the field distribution. Charge 2 is only trying to contribute its amount of charge. But you know the answer already, because E12 is already derived in the previous part point, right? It's just Q1 divided by 4 pi epsilon 0 R12 squared, right? This is E12, the field distribution created by the first charge. Because charge number 2 is seated R12 distance away from charge number 1. So this is where you put R12 squared. And that E12 is now multiplied by Q2. So this is Coulomb's law. It is saying if you have two charged particles, then they each exert some kind of force on each other. So the force felt by charge number 2 due to the presence of field created by charge number 1 is F12 will be this amount, this quantity. But at the same time, charge number 2 also creates its own field intensity pattern, and that field could also exert a force onto charge number 1, right? It's just a role reversed. You can imagine initially you have Q2 in space only, then you bring charge number 1 to this location. Exactly the same, it's just reversed. So in this case, Coulomb formulated the force felt by charge number 1 due to the presence of field created by the second charge would be having the same amount. They have the same magnitude, but the only difference is now the unit direction is reversed. Okay? So if these two charges are both positive, then E12 is pointing from 1 to 2. E21 is pointing from Q2 to Q1, so it's reversed. So this is really, again, nothing new. But what I'm trying to say is, Coulomb's law is really the direct analogy of Newton's law of universal gravitation. So now try to refresh your memory. You must be scratching your heads. Equal to m1 m2 r squared, right? You might have some coefficient, so let me just write proportional. They are basically the same.